we're talking about parallel and perpendicular lines in the coordinate plane. In order to do that, there's one concept that we need to start with, and that is the concept of slope. Slope is just a comparison of two numbers, specifically how high I am and over what horizontal distance I traveled to get to that height. So how far do I need to go left or right in order to attain a distance up and down? That's the question of slope. This distance up and down we refer to as rise. And this distance left or right we refer to as run. The rise and the run. And slope is always equal to a comparison of these two values. So, for example, suppose we had a filing cabinet. And I wanted to get on top of the filing cabinet. The filing cabinet is a fixed height. We call that the rise. Suppose further that I brought along a long plank or some other way of making a ramp to get up onto the filing cabinet. This distance here is called my run. So depending on the length of my plank or my ramp, I may have a very short run compared to the rise, or I could have a very long run compared to a given rise. And it's the comparison of that rise with the corresponding run that gives me this idea of slope. For instance, if I were to ascend onto the cabinet like this, you can see that I had a particular slope that I came up. If I move all these objects closer to the cabinet, like this for instance, and now I were to ascend up these objects, you'd find that my slope would be much steeper. Let's just take a look. Because in the second example, the horizontal distance I covered in order to get up on top of the cabinet was smaller. And so therefore we say that the slope was steeper. I ascended a relatively large distance vertically over a relatively short distance horizontally. We have to incorporate both of those ideas. Both the rise, how far up or down did I go, and the run, over which distance left or right or horizontally did I make that rise. And by definition, slope is equal to my rise divided by my run. Notice we could always quantify those values. If I wanted to talk about the slope of ascending the file cabinet, I could measure my rise, whatever the height of this cabinet is, and my run, whatever the distance is from my place on the floor there to over here. In a coordinate plane, I talk about rise as being my change in value on the y-axis. This is my y-axis, or my vertical axis. And my x-axis is over here, my horizontal axis. And so my rise is always equal to the change in value on the y-axis. Suppose we have these 2 points. I'll just assign them somewhat arbitrary values. We'll call this one 0, 6. And this one over here, we'll call 5, 11. 0, 6, and 5, 11. So if I want to talk about my rise is actually the change in vertical position. This is rise right here. And my run is the change in horizontal position. In order to be able to do calculations with this concept of slope, to be able to look at the numbers, we write slope this way. Slope is equal to y2 minus y1 divided by x2 minus x1. Now, we need to just look at one of these for a minute. Sometimes you'll see it described this way, that slope is equal to delta y over delta x. That delta, it's a triangle, it's a Greek letter delta. And in mathematics and in science, it stands for change in. Delta is change in. So what this really says, when I talk about delta y divided by delta x, it says change in y divided by change in x. And in order to understand the change in anything, for instance, if I say, hey, how has your height changed over the last year? The way you'd figure out the answer to that question is you'd take your current height and you'd subtract from it your height a year ago. Your current height minus your former height. That is height 2, your current height, minus height 1, your height last year. And so we do the same thing with these numbers in algebra and in geometry. My change in my y value, my change in my vertical value, which we call rise, is equal to my latter vertical value minus my former vertical value. Whatever that difference is, that's my rise. My run is found similarly. Change in x, which is change in my horizontal value, which is called run, is calculated by taking my latter x value and subtracting from it my former x value, and that difference is my run. And so we have this concept of slope. Notice slope always incorporates both rise and run. Slope cannot exist just because you know the height. You have to know the change in height and compare that to the change in horizontal distance. That's slope. So we have this idea of slope. Let's go ahead and calculate the slope of this line here that connects these 2 points. I missed, but I think you can use your imagination to work with me here. So I have a line that runs through point 0.6 and point 511. You'll remember by the line postulate, any 2 points define exactly one line. And there's that line. And so in order to find its slope, we'll just plug it into this equation. The slope of this line is equal to y2, which is 11, minus y1, which is 6, divided by x2, which is 5, minus 0. So slope simplifies to the following. 11 minus 6, which is 5, divided by 5 minus 0, which is also 5. You can see this fraction, we're all familiar with that. Slope is equal to 1. So we use a numerical value, 1 in this instance, to identify this particular slope. Now, in fairness to those of you who may be wondering, the slope of 1 actually should rise at a 45-degree angle. Because I'm not writing on any sort of graph paper, you can see that it's not perfect. So it should come up a little bit steeper than that. But I think you get the idea. In order to calculate slope, we need to compare the difference in the y values with the difference in the x values, and we do that by division. There's a couple more things I need to mention about slope. First of all, in mathematics, particularly in algebra, we typically use the variable m to represent the word slope. And you'll see that from time to time in different texts. M equals delta y over delta x, or m equals y2 minus y1 divided by x2 minus x1. So m is the variable we use for slope. So you'll see that regularly, and it's a shorthand. If you want to just write m, most people would understand that to mean slope. The second thing I'd like you to understand is that when I say that this is x2, y2, and x1, y1, that assignment is somewhat arbitrary. In reality, it does not matter which of those points I call 1 and 2. It doesn't make any difference. And remember, in geometry, there's really no up, down, left, right. It's just a geometric figure, and we use these values to calculate other values. So, let's just see if this works if we switch these. Suppose instead we call this x1, y1, and this one over here we call x2, y2. Let's just test to see if we get the same values here. So that means that to find slope, it'll be 6, which is y2, minus 11. And then I have 0, x2, minus 5. Let's simplify this. 6 minus 11 is actually negative 5, and 0 minus 5 is negative 5 as well. And negative 5 over negative 5 is the same as positive 1. Notice I'm not saying that the sign doesn't matter. The sign makes all the difference in the world. All I'm saying is that if you switch the points, you'll end up with exactly the same slope. And that's important to understand. One thing we cannot do, however, we cannot switch just the x values and leave the y values. So for instance, I could not take 11 minus 6, and then divide that by 0 minus 5. I can't take 11 minus 6 and divide by 0 minus 5. That's not going to work for us. Let's take a look. 11 minus 6 is 5. And 0 minus 5 is negative 5, which is equal to negative 1. Notice that's not the same as positive 1. Let's talk a little bit about the negative positive thing when we come up with the answer for slope. When I talk about a positive slope, the slope is ascending. More particularly, if I read the slope in a sense like I read a graph from left to right, and the slope is going up, I say that that's a positive slope. If when I read it from left to right, the slope goes down, we say that that's a negative slope. Let's look at one more example. I'd like to find out the slope of the line that connects these 2 points. So these are 2 distinct points. Remember, there can only possibly be one line that connects them. I'd like to know the slope of that line. I'll use this coordinate plane just as a tool for now, but then we'll do a problem that does not involve a coordinate plane just to show you that the process is the same. So we'll put the first point in there, and I'll just assign arbitrary values here. We'll say that that's equal to 1 unit, each of these marks. And so 4, 4 is somewhere in this neighborhood. Call that point A, and we'll call this one point B. So 0, 6 then is right here. And that's point B. Just to get an idea of what the line looks like, I'll connect those 2 points with a straight edge. And then you can see the graph of the line AB. Already we can tell that the slope is negative. Why? Because as the line goes from left to right, it goes down, and so we say that it has a negative slope. Let's just check the numbers and see if that's correct. To find the slope of AB, remember that slope is equal to y2 minus y1 divided by x2 minus x1. Therefore, in this instance, slope is equal to y2, which is 6, minus y1, which is 4, divided by x2, which is 0, minus x1, which is 4. And we need to simplify that a little bit. 6 minus 4 is 2, and 0 minus 4 is negative 4. So you see the answer when we simplify it here is negative 1/2. And that is our slope. Notice the negative sign. It says that the slope goes down as we go to the right. And the 1/2 also tells us that the slope is not as steep as the last one we looked at, which was a 1 at a 45-degree angle. So the sign and the magnitude tell you a lot about a slope. Let's run through another example in which we're not going to look at the coordinate plane. Let's just see if we can calculate the slope by itself with the numbers. Suppose I want to know the slope that passes through these 2 points, 8, 3, and 4, 11. To find slope, we simply say that slope is equal to y2 minus y1 divided by x2 minus x1. We'll just plug these numbers into their appropriate places in the equation. Slope equals 11 minus 3 divided by 4 minus 8. We need to simplify this a little bit. 11 minus 3 is 8, and 4 minus 8 is negative 4. And so you can see we end up with 8 divided by negative 4, which equals negative 2. And that is my slope. So that's how we calculate slope algebraically. We can also read slope in a graph. Here in the coordinate plane, you'll notice there are 4 points, which I have named A, B, C, and D. And I'd like to know something about their slopes. The easiest way, perhaps, is just to get the values of the points and do it algebraically, as we've already looked at. But suppose you just want to take a quick look at it and see if you can figure it out from the graph. It's actually not that difficult. To begin, I'm just going to draw in some lines. Suppose we want to talk about line AB and its slope. And then we want to talk about CD and its slope. Talk about AB first. In order to quantify the slope, you look at rise and divide it by run. So in a particular interval, what is the rise? Let's just go from A to B. You can see we have to rise 1, 2, 3, 4 units. And then the run, that is how far we move left and right, is 1, 2 units. So my slope is equal to 2. With respect to CD, again, we look at rise and we look at run. My rise here is actually negative, 1, 2. And my run appears to be from here to about there. It looks like it's 4. 1, 2, 3, 4. So here I have negative 2 over 4, which is equal to negative 1/2. So whether I do it algebraically or graphically, it's still a comparison of rise and run. Anytime we talk about slope, we're talking about a comparison of rise and run. Now, so far I've talked about slopes being positive and negative, But there are two other particular slopes we need to be aware of, which are neither positive nor negative. They're special. We need to talk about those. Those are the slopes of vertical and horizontal lines. So if this is my coordinate plane, suppose I look at this line right here. Let's just stipulate that it's a horizontal line. Let's stipulate that it's perpendicular to the vertical axis and parallel to the horizontal axis. We'll call that y equals 4. You can see that anywhere on this line, the y value, the vertical value, is 4 units above the x-axis, no matter where I go. So if we were to pick 2 points, such as this one and this one, let's suppose this is, well, we don't have to suppose, it's pretty obvious. This is actually the point 0, 4. And this one over here, let's just suppose it's 9, 4. 0, 4 and 9, 4. We could ask the question, what is the slope? What is the slope of this line? We know how to calculate slope. It's rise over run, delta y over delta x, y2 minus y1 divided by x2 minus x1, however you want to think about it. Let's run the numbers and see what we get. When we build the fraction, we have 4 minus 4. I could probably stop right there. But let's just finish it out. 9 minus 0. You can see the denominator, of course, comes out to be 9. But the numerator is 0. And that's why I said we could probably stop right there. Because no matter what the denominator is, if the numerator is 0, then the value of this equation, this fraction rather, is also 0. And so we say that horizontal lines always have a slope of 0. We quantify it. We say there is no slope, which is just another way of saying there is 0 slope. So if you think about being in a really large parking lot that's perfectly flat, and someone said, hey, what kind of a slope does the parking lot have? You'd say it doesn't have a slope. It has 0 slope. Okay. Let's look at one other type of line. Let's look at a vertical line, such as this one. We'll just stipulate that this is the vertical line x equals 6. So this point right here must be 6, 0. And we'll just pick some other random point on here. Suppose this is 6, 10. 6, 0, and 6, 10. Notice that any point on this vertical line will have value x equals 6. All of the x values are 6. So let's just calculate the slope if we can. Again, the formula is the same. y2, 10, minus 0, minus y1, divided by x2, minus x1. And you find that you end up with 10 divided by 0. Now, mathematically, that's a problem. In algebra, we say that this value is undefined. It doesn't have a definition. We really can't wrap our minds around it because it's hard to divide anything by 0. It can't be done. So we say that that slope is undefined. Horizontal slopes we quantify at 0. Vertical slopes we say are undefined. So it's important to remember that these slopes have special characterizations. Horizontal lines have slope 0, vertical lines undefined. And again, you'll look for that 0 in the denominator. That's a good indicator that you're dealing with a vertical line which has a slope that is undefined. Now we've already talked about this idea of parallel lines. Parallel lines. We know that those are coplanar lines that never intersect. When we talk about graphing parallel lines in the coordinate plane, the thing that we always find is that parallel lines always have the same slope. They always have the same slope. That is, for every unit of rise, they have the same unit of run. Parallel lines always have the same slope. And that's close to a definition that we have in the coordinate plane for parallel lines. It's one of the pieces of information we need to throw in there. Parallel lines have the same slope, but they also must have different y-intercepts. Of course, if their y-intercepts are the same, that is, if we were to bring this line down to here, well, we find, in fact, we're talking about the same line. They have the same slope and the same y-intercept. So parallel lines have the same slope and different y-intercepts. Same slope, different y-intercepts. That makes it pretty easy for us to begin to analyze lines and ask the question, are two lines parallel? Before we do that, let me just remind you of something you probably learned last year in algebra, and that is something called the slope-intercept form of a linear equation. Slope-intercept form. Remember, a linear equation is any equation that has a graph which is a straight line. And when we talk about the form of an equation, it just means the shape. It means that we've arranged all the parts in a very particular place. So we say that it's in a particular form. And when we talk about slope-intercept form, we're talking about a form in which we can immediately or directly read slope and intercept. That is y-intercept, to be more particular. A slope-intercept form of a linear equation is in the form y equals mx plus b. We already know what m is. M is the slope. I said that earlier. And b is the y-intercept. So if I'm given the equations of two different lines, and I'm asked the question, are the lines parallel? All I need to do is look at the slope and look at the y-intercept. If the slope is the same and the y-intercept is different, then they're parallel. If the slopes are different, then they're not parallel. They couldn't possibly be. If the slopes are the same and the y-intercepts are the same, then it's actually the same line. Let's just look at a couple of examples real quick. Here's the first example. These are two equations. They are linear equations. They're in the form y equals mx plus b, so in slope-intercept form. I can look at them and say, hey, on this first equation here, this is the slope and that's the y-intercept. And on the second equation, this is the slope and that's the y-intercept. And if I ask the question, are they parallel? The answer to the question is yes. How do I know? Because they have the same slope, that is, they have a similar rise and run, or a proportional rise and run, and they have different y-intercepts. We could graph them real quick just to get an idea of what that looks like. And I'm just sketching this. I'm not trying to make it perfect. But if I wanted to graph this equation, remember I start with the y-intercept. 1, 2, 3, 4. And then I go to slope. So my rise, slope of course here is equal to 3, which is 3 over 1. My rise is 3 units with a run of 1 unit. Up 3, 1, 2, 3, over 1. And so the line would look like this. The next equation is a y-intercept of -2. That's down here. There's my y-intercept. And my slope again is 3, up 3, over 1. And there's my line. And you can see that the lines are parallel. So these are the numerical values I look at to determine whether my lines are parallel in the coordinate plane. Same slope, different y-intercept. All right, several more examples here. And the question that we're asking, or trying to answer, is, are these lines parallel? Are the lines represented by these equations parallel in each of these problems? We should be able to fire through them pretty quickly, mainly because all of these equations are written in slope-intercept form. So all we need to do is look at the slopes and ask, are they the same? And if they are, then ask whether the y-intercepts are different. So let's get started with number 2 here. Here we can see that we have a slope of 1/3 and a slope of 2/3. So those are not parallel lines. They have different slopes. Their slopes are at different angles. Here we have 3x and 3x, so that works. Same slope. But their y-intercepts are different. That's also good. And so that is, in fact, a set of parallel lines. Number 4, different slopes. Those are not parallel. Number 5, same slopes. That's good. Same y-intercepts. And in fact, when you look at this, you see they say the same exact thing, y equals 5x plus 2, y equals 5x plus 2. Those are not parallel lines. That's actually a single line. It's just been written twice. Number 6, 1/8 is the slope on both of these. Same slope, different y-intercept. Those are parallel lines. Number 7, Number 7 is a little bit different because the slope is not written in here. So we have to ask the question, what must the slope be? What number is being multiplied by x here? The answer to the question is the number 1. The 1 can be inferred. We don't normally write it because it gets kind of tedious. Since I could write 1 in front of every variable, and in fact, I could write 1 again in front of these variables to say that it's not just 1x, but it's 1x. Okay, that gets ridiculous. So we don't write the 1. But it's still inferred. which means that these do have the same slope. They do have different y-intercepts, therefore those are parallel lines. What about number 8? In number 8, we have something missing over here, at least it seems so. And so we have to, again, make an inference. I'm asking the question, what number is being added to or subtracted from 2x in this equation? The answer is 0. We can infer the 0. We never write it because, again, that would get tedious. We could write plus 0 anywhere we wanted to. It's somewhat meaningless. So we don't write it, but understand that it can be inferred. So here we have y equals 2x plus 0 and y equals 2x minus 2. Same slope, different y-intercept. Those are parallel lines. This last example is maybe even a little bit more difficult. Y equals 3 and y equals 7. It does not appear to be in slope-intercept form, although technically you could make an argument that it is. The question then is, what values were multiplied by x in order to get those equations? And I think you'd have to agree with me that it must have been 0. It was 0x and 0x. And that's why I never wrote the x's, because 0 times x is nothing. And 0 times x down here is nothing. And so we end up with y equals 3 and y equals 7. Both of these, you should recognize, are horizontal lines. How do we know? Because the slope is equal to 0. Therefore, since they're both horizontal lines, with different y-intercepts, they are in fact parallel. All right, the next thing we need to do is talk about the slopes of perpendicular lines. Slopes of perpendicular lines. Remember, we're still working in the context of a coordinate plane, and we're still looking at both the graphical and the algebraic representation. The graphical is what we draw on the coordinate plane. The algebraic is when we write the equations. And we're still dealing with linear equations, and we're still looking at them in slope-intercept form. And we know that that is the form y equals mx plus b. Okay. So the question for us now is, what about perpendicular lines? How would their slopes compare? The answer to that question is that the slopes of perpendicular lines are always what we call opposite reciprocals. Opposite reciprocals. Now we need to unpackage that a little bit. We ask the question, what does opposite mean? Well, when you think about numbers, that's always positive and negative. So for instance, 3 and negative 3, those are opposites. Or negative 7 and positive 7, those are opposite numbers. 13 and negative 13. Or numbers like 1/2 and negative 1/2. Those are all opposites. They just have an opposite sign. That's all. One's positive and one's negative. What about reciprocals? We've dealt with opposite, but what about reciprocals? What does that mean? Technically, the definition of reciprocals are two numbers that when multiplied have the product 1. So for instance, if I take 1/2 and multiply that by 2, I get an answer of 1. Or if I take the answer 4 and multiply by 1/4, I get the answer 1. So 2 and 1/2 are reciprocals. 4 and 1/4 are reciprocals. So let's look at some other examples. One of the easiest way to identify reciprocals is just take a fraction and flip it upside down. That'll produce the reciprocal. So if I look at 1/2, I flip it upside down, I get 2 over 1, which we know is simply 2. If I have the number 1/4 and I flip it upside down, 4 over 1 is the reciprocal. If I have a number such as 8 and I flip it upside down, 8 of course is 8 over 1, 1/8. Or a number such as negative 7. That's the same as negative 7 over 1. If I flip it upside down, I get 1 over negative 7. And of course that is equal to the same as negative 1/7. Okay, so I have this concept of opposite and a concept of reciprocal. And when I'm talking about the slopes of perpendicular lines, I find that their slopes are always opposite reciprocal. I need to incorporate both of these ideas. So if I have a number like 1/2, and I ask what is the opposite reciprocal of 1/2, well the opposite is negative 1/2, and the reciprocal of that is negative 2. I get negative 2. If I have a number such as 4, Well, the reciprocal of 4 is 1/4, and the opposite of that is negative 1/4. Negative 1/4. Now, doing it like this, going from a fraction to a whole number, or a whole number to a fraction, may be a little bit difficult. So it may help sometimes, by the way, that's not a whole number, it's an integer. It may help just to draw the 1 underneath there. If that helps you, that's perfectly fine, there's no problem with that. You just draw the 1 underneath, then flip it upside down and put the opposite sign. So what about a number such as negative 1/2? How do I deal with it? Well, the opposite of negative 1/2 is positive 1/2, and the reciprocal is 2. 2/1. So when I'm trying to ascertain whether two lines are perpendicular, it's a similar process to finding out whether they're parallel. I first look at the slopes and ask, are the slopes opposite reciprocals? Let's take an example. Here we have two linear equations. They're both written in slope-intercept form. I can see y equals mx plus b. B, by the way, is negative 3 here, if you're wondering. And I ask the question, are they perpendicular? In other words, are the slopes opposite reciprocals? Well, if I look at this slope 1/2, the opposite of 1/2 is negative 1/2, and the reciprocal of negative 1/2 is negative 2. So sure enough, I find that those are perpendicular lines. And that's the algebraic test. If we're asking the question whether two lines are perpendicular, we first look at the slopes. If the slopes are opposite reciprocals, then the lines are perpendicular. Notice in this test, the y-intercept doesn't really matter. Even if they had the same y-intercept, they'd still be perpendicular lines. And we can see that if we graph the lines in the coordinate plane. Again, just as a rough sketch, since we don't have graph paper here. If I were to graph this line, y equals 1/2 x plus 2, notice the y-intercept is 2. Let's say that this is 2 right here. And the slope is 1/2, up 1 over 2. Up 1 over 2. There's my line. When we graph the second line, we notice that the y-intercept is the same. That's the same point here. But the slope is negative 2. Down 2 over 1. So we'll go down 2 and over 1. That puts us here. Just because they have the y-intercept doesn't mean they're not perpendicular. So when I'm asking the question whether the lines are perpendicular, I need not worry about the y-intercept. All I need to pay attention to is the slope itself. That sums up what we need to know about parallel and perpendicular lines in the coordinate plane. Make sure you find some practice problems just to test your understanding. And as always, if you have any questions, send me an email.